Hello students, in the last lesson we learned about the rotor support scheme of a single rotor engine. In this lesson we will learn about the rotor support scheme of a dual rotor engine. Most engines before the 1970s adopted a single rotor structure design. With the continuous improvement of engine aerodynamic performance, most engines now adopt a dual rotor or triple rotor structure design. The multi-rotor engine has put forward many new requirements for the design of the rotor support scheme, which are mainly reflected in the following two aspects. First, the multi-rotor engine has a more complex structure due to the large number of rotors and supports, and the low-pressure rotor shaft must pass through the center of the high-pressure rotor. However, in principle, the rotors of the engine can be separated, and each rotor can be analyzed and processed separately according to the above method. Second, there is a rotor structural system, in which the supporting structure is not directly installed on the load-bearing casing, but is installed on another rotor through a special bearing. The load is transmitted through the fulcrum of the other rotor, so we call the two bearings between the rotors intermediate bearings. As shown in the figure, the advantage of having an intermediate fulcrum is that it can reduce the number of engine load-bearing frames from 4 to 3, and the length of the engine is also relatively shortened, so intermediate bearings are widely used in aircraft engines. Next, let these learn about the rotor support structure of the WP7 engine. WP7 is the engine with the fewest stages among twin-rotor engines. The high-pressure and low-pressure compressors have 3 stages each. The low-pressure rotor adopts a 1-2-0 support scheme, and the high-pressure rotor adopts a 0-2-0 support scheme. A feature of the WP7 engine support scheme is that the support system uses 2 intermediate fulcrums, that is, the last 2 fulcrums of the low-pressure rotor are supported in the high-pressure rotor, and its load is transmitted to the outside through the support points of the high-pressure rotor. This structure shortens the engine length, reduces the load-bearing components, and reduces the overall structural weight. Another feature of the WP7 engine support scheme is that the loads at the 3 fulcrums are all transmitted through the stator blades, or the load-bearing parts inside the blades, without using an additional load-bearing casing, which further shortens the length of the engine and simplifies the overall structure. However, the load-bearing components of the cantilever rotor are located in the high-temperature area in front of the turbine, which makes the working conditions worse. Next, let these look at the CFM56 engine produced by GE of the United States and SNECMA of France. The CFM56 engine is a high bypass ratio turbofan engine. Its 2 rotors are supported on 5 fulcrums, and the bearing load is transmitted to the outside through 2 sets of load-bearing components. It is an engine with the least load-bearing components. Its low-pressure rotor adopts the 0-2-1 support scheme, commonly used in high bypass ratio engines, and the high-pressure rotor adopts a 1-0-1-2-point support scheme. The reason for fewer load-bearing components is that the rear shaft of the high-pressure turbine is supported on the low-pressure turbine shaft through an intermediate support point. This support method can shorten the axial size of the engine. However, this method of supporting a large diameter high-pressure rotor on a smaller diameter low-pressure rotor will affect the operation of the high-pressure rotor due to vibration or deformation of the low-pressure rotor. For this reason, although a 3-point support scheme is adopted for the low-pressure rotor, a widget coupling is used to connect the low-pressure turbine shaft and the fan shaft. This requires improving the machining and assembly accuracy of the rotor and the casing to ensure that the rotor has a high concentricity in the casing bearing system. In order to reduce the span between the 2 supporting points of the high-pressure rotor, the front shaft diameter of the rotor is derived from the 3rd stage compressor wheel, so that the bearing of the front supporting point generally does not exceed the axial position of the first stage moving blade. This can minimize the span between the two supporting points. Reducing the supporting span is beneficial to improving the bending stiffness of the shaft. In summary, the main feature of the engine with intermediate bearing designed by GE is that it can save a load-bearing frame, thereby shortening the axial length of the rotor and reducing the weight of the engine structure. However, the intermediate bearing between the two high-speed rotating shafts is difficult to supply oil seal and assemble. Since the high-pressure rotor is supported on the low-pressure rotor, the vibration between the rotors has a greater impact, which needs to be fully considered in the rotor dynamics design. In addition, for a twin rotor engine with an intermediate bearing, the intermediate bearing will cause mechanical contact between the high-pressure and low-pressure rotors. Its main effect is to correlate and influence the vibrations of the two rotors, so, when using the intermediate bearing, the mutual influence between the rotors should be minimized. In structural design, it is generally only used in engines with a single-stage high-pressure turbine. Students, in this class we have learned about the rotor support scheme of the twin rotor engine, focusing on the support scheme of the engine with intermediate bearings, and analyzing its structural characteristics. I hope that students will review it in time and learn from it. Thank you.